Hello, and welcome to our webinar where we will learn how machine learning helps Levi's leverage its data to enhance e-commerce experiences. Let's take a brief look at the outline of our broadcast today. We will start with the story of AI as seen from within the organization where most machine learning takes place than anywhere else. We will then transition to our Amazon Partner Network Competency Partners, Dataiku, and learn about Dataiku's inclusive AI. And finally, we'll hear from our guest of the hour, Levi's, and delve into the fascinating journey of how their recommendation systems evolved from version 1 to the one that is deployed in production right now. Let's take a look at the speakers that we have lined up for today. Along with me, we have Will Novak, who is a data scientist at Dataiku. Dataiku is an APN competency partner, and as they termed it, it is a match made in machine learning heaven. Dataiku's mission is to provide organizations with technological environment that enables all people throughout an enterprise to use data by removing friction surrounding data access, cleaning, modeling, deployment, and more that allow for successful operationalization. And our guest of honor today is Pallav Agrawal. He is the Director of Data Science at Levi's. Levi Strauss & Co. is an American clothing company known worldwide for its Levi's brand of denim jeans. It was founded in May 1853 in San Francisco, and today we'll see that it is also a place where cutting-edge machine learning is being deployed to derive product recommendations in real time. Levi's, as they like to say it, is the original Bay Area startup. And me, I am Chaitanya. I am machine learning specialist solutions architect with AWS, and I'll be your host during this webinar. Now, let me take this opportunity to set the stage for our deep dive. Customer and partners choose AWS over other providers because it has more functionality, the largest and the most vibrant community of customers and partners, the most proven operational and security expertise, and the business is innovating at a faster clip, especially in the areas such as machine learning and artificial intelligence, Internet of Things, and serverless computing. Machine learning at Amazon has been an active area of investment and research for the last 20 years. We have innovated, improved, and published original work in the area of machine learning for the past 2 decades, be it in the area of fulfillment and logistics, like in the case of our warehouses using Amazon robotics to streamline package creation, or in search and discovery in Amazon retail, or in topic modeling in lengthy tomes, making content more accessible, or the upcoming Amazon drone delivery system, Prime Air, which is fully operational trial operating near Cambridge, United Kingdom, or be it amazing natural language processing capabilities of Amazon Alexa or Amazon Go, a brand new retail store concept that is operating across the US. Amazon has been an innovator in the field of computer vision, forecasting, search and recommendations, natural language processing, autonomous drones, and applications in retail, amongst other areas. It is interesting to note that I mean, that machine learning has been around for more than 50 years. Most of the common machine learning techniques that we use today were really invented decades ago. What has changed recently is that with cloud computing, AI and machine learning have become accessible to all businesses, not limited to just the major tech giants and hardcore academic researchers. Cloud has removed so many barriers to experimenting and innovating with AI that even risk-adverse businesses are making it part of their strategies. So we are seeing a tipping point where the recent hype for these technologies is transitioning into real impact on business. A recent IDC study estimated that this year, 40% of digital transformation initiatives will take advantage of AI. IDC also predicted that by 2021, global spending on AI and cognitive technologies will exceed $50 billion worldwide. So what's our mission? By the way of deliberate osmosis, we want to enable our partners and customers. We want to take our rich experience with machine learning across Amazon and put it in the hands of all organizations, every developer, data scientist, and researcher. And how do we do this exactly? We are uniquely customer focused. We start with the customer need and work backwards. 90% of our AWS roadmap is built directly from customer feedback. We are unmatched in the breadth of ML services we offer to our customers today. We believe customer choice and flexibility are incredibly important. We support all popular frameworks and interfaces to give you choice and flexibility. We also have the deepest set of security encryption features with broadest accreditations. And our approach to R&D is fundamentally different and unique. Our scientists are embedded with our product and engineering teams, and we invent and simplify on the behalf of our customers. As a result, more ML happens on AWS than anywhere else. Why? Because we have the broadest set and deepest set. We have the broadest and deepest set of capabilities. We see machine learning stack as having three key layers. ML frameworks, that is the bottommost layer for machine learning practitioners, researchers, and developers. This includes infrastructure. AWS offers a broad array of compute options for training and inference with powerful GPU-based instances, compute and memory optimized instances, and even FPGAs. Then we have the ML services. Amazon SageMaker removes the heavy lifting, complexity, and guesswork from each step of the machine learning process. SageMaker makes model building and training easier by providing pre-built development notebooks, popular machine learning algorithms optimized for petabyte scale datasets, and automatic model tuning, enabling developers to build, train, and deploy models in a single click. Finally, we have the AI services which are ready-made for all developers, no ML skill needed. They cover the areas of vision, speech, language, chatbots, forecasting, and recommendations. Now let's talk about the topic of the day, topic of this webinar, recommendation. Now let's zoom out and switch gears. Recommender systems were first described in a technical report as digital bookshelf in 1990 by Jesse Carligan at Columbia University. In this report, he talks about how in a typical bookcase for any reader, interesting documents often happen to be found adjacently to each other. He also further states that it might be difficult to get people to agree on which books are interesting and which are not, but everyone will find an interesting corner in the bookcase. Apart from being omnipresent, they are also a favorite topic of mine, as like you would have guessed by now. I can geek out on it for hours. I would rather talk about normalized discounted cumulative gain and mean reciprocal rank than anything else. Recommendations more importantly drive about 30% of traffic to Amazon.com. Given the amount of traffic Amazon.com receives, it's actually a very significant number. Recommendation engines deal with solving various machine learning problems that apply the solution at scale. They typically deal with how to represent real world objects in vector form, how to group users together via similar interests, how to follow user activity in temporal dimensions, and revolve suggestions based on that. Today, Pallav is going to take us through a deep dive on the recommendation systems, their applications, and importance. He is also going to talk about evolution of recommender systems as Levi's and how data EQ plays an important role in enabling data science teams at Levi's. Data IQ is our APN machine learning competency partner. AWS competency is our global partner program designed to promote and highlight our top AWS partners based on their overall specialization in key AWS solution, workload, and vertical areas. Our goal is to be the most customer obsessed partner program by providing our AWS customers with top vetted and validated partner solutions that can help customers take advantage of AWS products and services. AWS competency partners go through rigorous technical assessment and verification of their expertise specific to each AWS competency. Without further ado, I would like to invite Will from Data EQ to give us a tour of Data EQ's inclusive AI platform. Over to you, Will.
Great, thanks so much, Tanya. So as noted, Dataiku is a data science platform that's been around since 2013, so not quite as long as Levi's back in the 19th century, but we've been doing this for a good long time, and inclusive AI has been at the core of our mission and value proposition from the start. So as noted, I'm a data scientist at Dataiku, which entails helping our clients and partners get up and running and architecting anything from their data science infrastructure all the way to building out particular use cases, very much like the recommender system that we're going to talk about today. So before we talk about inclusive AI, we should mention this concept of enterprise AI, which is something that is very meaningful to us at Dataiku. So in particular, enterprise AI, as we view it, is all about scale. So as you can see, we're aiming to augment 100% of business processes for the benefit of 100% of an organization's employees. So in the past, this idea of siloization is something that I will refer to again and again throughout my presentation today. In the past, and to some extent still in the present, we see organizations far too often being siloed in their work and siloed in their attention to AI and how it can benefit the business. But for us at Dataiku, we see enterprise AI as holding the promise of really augmenting and improving and touching every aspect of the business. And we'll talk about how exactly we at Dataiku enable that. But before we do, this concept of data project silos and the individual personas or roles that oftentimes play a part in a data project is one that we should touch on first. So as you can see here on the left, we have 3 different personas that we often talk about at Dataiku, namely the business analyst, the data scientist, the data engineer, and of course there are other individuals that are involved in a data project that I'll talk about a little bit further on. But this is kind of one way that organizations might go about thinking about their data project. So you have some sort of analyst, their job is maybe working in SQL or Excel, they're accessing the data, they're preparing the data, they're getting it ready, and then they're typically doing a handoff. And so that handoff here you can see indicated by red X's. Why do we use red X's? Because oftentimes those handoffs, they're not so seamless. So whether it be technically challenging in some way to perform the handoff of assets and communication, or otherwise, whether just information gets lost in that process, the handoff is a real risky area. And so at Dataiku, as we'll discuss, by bringing all of these personas in one shared platform, we help resolve those handoff issues. But in this case, in the traditional workflow, a business analyst might pass that work then on to a traditional data scientist who's maybe working using tools such as Python, R, MLlib, Scala, what have you, and they're really focused particularly on the machine learning modeling piece. And then once they have some prototype and they have some MVP, also we sometimes see that organizations in their architecture is not set up for the data scientist to push that work seamlessly into production, but instead it needs to again be pushed to a different persona, in this case the data engineer, who refactors the work, and then we'll push that off perhaps to an API platform. And so again, this idea of siloization is a risk. Also this idea of exclusive AI, where we oftentimes rely on maybe that central data scientist who does indeed have expertise, but they work in a sort of black box, excluded way. And at Dataiku, we want to really promote inclusion, bringing multiple voices to the table, making sure that everyone understands the white box solutions so that they can add value to the entire organization. And to further touch on all the personas involved, it should be noted that it's not just, as you see in the center, the data analysts, the data engineers, and the data scientists. Of course, in a technical space, as you see on the right, we have IT constraints. So there's an entire fleet of IT individuals, whether those be partners, whether if you're using cloud solutions or some local team as well. They need to be involved in the data project to be sure. And then, of course, as in enterprise AI, we're looking to drive business value and augment 100% of business processes. Of course, we have business leaders, business project sponsors, and data consumers who are all also involved in this process. And so again, if everything lives in isolation, then there's risk of miscommunication, there's risk of project not going off as so desired, whereas if everyone's on the same page, if communication is more seamless, then we're going to have an easier time of aligning priorities, which is exactly what we're hoping to enable. To further dwell on this idea here, you can see a quote from John Hennessy, the chairman of Alphabet, who notes that ML is the ultimate garbage in, garbage out technology. So in this case, ML can be garbage in, garbage out, and that's particularly a risk, again, if we have exclusive data science. If we have individuals who don't really understand the domain, but they just understand the models, then even if the model's high performing, from a business sense, it really can be garbage in, garbage out. And so to alleviate that, you can see that MIT has spent or is spending $1 billion to start an AI college, and their mission is to educate the bilinguals of the future. And so in this case, the bilingual, on one part, these bilinguals understand AI, they understand data science, they understand computer science, but they also need to have another skill set. That is, they need to also understand the domain they're working in. And so at Dataiku, we provide a tool so that individuals with that crucial domain knowledge can participate. And not only can they participate, they're encouraged to do so. At Dataiku, this gives you a little bit more detail about how we actually think about this. On the left, you could see an analytics leader managing a team perhaps of business analysts, data scientists, and data engineers. But on the right, we have a high-level architecture diagram of what exactly Dataiku is doing to enable this. So if you squint your eyes, you can see here we have Hadoop, NoSQL, images, text, voice, whatever your enterprise data store, or stores, I should say, plural, we can interact with all of them. We bring in disparate data sources into one central server-based platform where we enable all of these users to communicate, to engage in data management, machine learning, and indeed model deployment. So ultimately, we want to drive model deployment to make sure that the organization is getting value from that ML model. And as you see on the right, this can be deployed on premises or in the cloud. So Dataiku really maximizes flexibility for our clients, and we'll talk about how exactly Levi's has done just that. Lastly, you can see here, if you look from left to right, a typical data science project entails data management, machine learning, and model deployment. And if you follow all the arrows, indeed, you can see that perhaps if you focus on the purple, the business analyst doesn't just appear once and then disappear, but rather a business analyst in Dataiku might be involved in visual auto data preparation, which you can see on the left. But at the same time, in the center, you can see that that same business analyst might use Dataiku's visual auto machine learning tools or Dataiku's visual pipeline to be involved in things that were in the past restricted to data scientists or data engineers. In the middle upper left, you'll see the traditional data science role might be doing some behind the scenes coding work in Dataiku, developing what we call plugins to further enable individuals in their organization to do things just like data preparation, just like data visualization, and just like machine learning model building. So all these roles are constantly involved in the end-to-end flow of a data science project. And so with that, I'll pass it along, and so we can hear really how this has worked in detail with great success at Levi's.
Thank you, Will and Chaitanya, for the introduction and the kind words, and also for providing the infrastructure and platforms that has helped us, actually build the recommendation systems that improve our customer experience at Levi's. So, not sure how many of the attendees are not aware of Levi's, but in case someone's not, Levi's, as you all might have be aware of, that is a denim brand. Make products for people across the globe, and along with our wholesale channels, we also have our e-commerce channels where we we can sell directly to our consumers. And what we're going to talk about today is really about how we made the customer journey more intuitive and frictionless by the use of product recommendations. So just as a little bit of background, Spotify, which millions of people use across the world, has this feature named Discover Weekly, where they create a personalized playlist for each of their users, and they create tens of millions of playlists, a week, and billions of songs have been discovered, or billions of songs sort of like have been played due to this. And it's one of the most important features that they have, and sort of like one of the main competitive advantages that they offer. Amazon, on the other hand, similarly has a different type of recommendation system. And I think most people, when they think of a recommender system, probably think of something like, customers also shop for the carousel that we see below a product page, on a product page. And the amazing statistic there is that about 30% of the product views at Amazon come from their recommendation carousel. And these are examples of some of the best recommendation systems out on the internet. And what they've done is that they've created an expectation for consumers to have a highly personalized experience when they're shopping online, or where they're just like, when they're browsing online. And this was actually verified by a Bazaar Voice consumer survey last year, where they said that they surveyed several thousands of people. And what they found was that most people are actually interested, or they would like to see a personalized experience when they're online. But the number of people who actually experience a personalized homepage is half of that. So, for example, in apparel, which is the space that Levi's plays in, the need for a personalized experience is about 44% of all consumers who are surveyed, but the actual feedback is that people who have experienced is only about 23%, so about half. And the other interesting factoid here is that 38% of the consumers say that they would not return to an online retailer who recommends things that don't make sense for them. So the onus of getting, a recommendation system to work correctly is really on the retailers. And it's not just about just checking a box of saying that, hey, I've put a recommendation system online, but it's actually how do we make that customer experience meaningful and really relevant for the end consumers. And so when, as the machine learning team, when we were thinking about, how do we want to enable a personalized experience online, we actually found great inspiration in our store associates who run out several hundreds of ours, Levi's brick and mortar stores. And what we do is that we get a lot of feedback from consumers. And one piece of feedback that I would just like to highlight here, because I think is super relevant, is for a stylist named Tanner. And the feedback was Tanner was super friendly and helpful from the moment we walked into the door. He was very knowledgeable about the different styles and helped me find exactly what I was looking for, even though I wasn't expecting to find it. He made the experience so much better, and I found some amazing pieces. Thank you, Tanner. Um, Now, really, what we tried to do was that we looked at this feedback and several other. This is just one sample that we picked from thousands of such feedback that we get on a daily basis. And really, what we were trying to think of it as that ideally our recommender system online should be one that when somebody uses it would give similar they would give similar feedback to it. Instead of Tanner, they would say the Levi's recommendation engine was super friendly and helpful. And so what we tried to do was we tried to isolate what are the key attributes of a good consumer experience. And I think one thing that we found was, I think what's highlighted in yellow here is that it was super friendly and helpful. So primarily it has to be helpful. The system has to have the knowledge embedded in there of the products. It should help the consumers find what they're looking for, but it should also have an element of serendipity where the consumers might be able to find something that they might not know they wanted. And we did some consumer insights surveys, and we did a lot of testing to then really nail down the 5 most important qualities that makes a recommendation system good and really enables a good personalized experience for the end consumer. So the first one is that the recommendation system should make the consumer journey intuitive and frictionless. The end goal, I think a lot of times when companies look at recommendation systems, they focus a lot on metrics like accuracy, mean average precision, NDCG, etc. But really, the core metric that we should be looking at is that how much friction is this recommendation system is this reducing for the end consumer. So, for example, when you land on a homepage at a website, you know you want to be you're landing there with some kind of intent. Now, your intent might be to shop for yourself, to shop for somebody else, might be just to like price browse, whatever, right? You could have any number of intents. How easily can I get you to your goal, and how easily can I, you know, get you from point A to point B through the recommender system should be the main focus of a good recommender system. The second quality is that it should reflect and communicate the organization's brand values. And what we mean by that is that we should not let a lot of times when we deploy algorithms, those algorithms are optimizing for some metric. Again, that could be accuracy, conversion, whatever. But in the pursuit of optimizing those metrics, we should not forget the brand values and how the brand chooses to communicate with its consumers. Because at the end of the day, a recommendation from a recommendation carousel should feel like an expression of the brand, and it should feel like something that the brand itself would recommend to people. The third quality would be that it should really focus on what consumers want and not on who they are. And so a lot of recommendation systems try to, have the experience of, okay, tell me more about yourself. Like, what's your age, what's your location, and it tries to collect a lot of information about consumers. And I think that while that is useful, it's still not an individualized experience, because if you think about the points of information I can capture about somebody, let's say age, location, gender, there are probably for any such combination, there are thousands of people like that. So just that itself may not be necessarily what's super useful. What might be more useful is that if the recommender system is able to understand what is it the consumer wants to do, and then help them get to that faster. It should be able to also utilize both implicit behavioral markers and also take in explicit inputs. And and then also it should be able to provide relevant information in a timely manner to expedite decision making. And really, what at the end of the day, the decision to make a purchase is on the consumer. And a recommendation system, like when it works well, should be one where it can provide that relevant piece of information that the consumer wants, that then helps them, you know, make the decision that whether they want to, buy this product or not. And if we can encompass all these qualities, then we would then basically from our team standpoint at Levi's, we feel that we could actually build a good recommender system. And so let's take a quick view of how we actually evolved and how we went through the process of building, a really good recommender system in-house. So the story starts, several years ago when we deployed a recommendation carousel from a third-party vendor, and it was on the website, and I think it did fairly well. But when we did some consumer insight studies, what we found was that certain areas for the recommendation experience stood out as a negative for the end consumers. The first one was the title, which says recommended for you. And one of the most common pieces of feedback that consumers gave was, why is it recommended to me? And based on what information about me is this based on? And this actually, in the recent times when privacy has become more hot button topic and more relevant for our consumers, based upon what information becomes a very important question. And right now, the title did not necessarily explain that. The second thing that you might notice is that as a denim company, obviously we sell a lot of jeans, and then you see a male jean, and then suddenly a female jean appears, and then it's again followed by male jeans. And so consumers, and this was a common experience, and consumers were often confused as to why, if it's saying that this is recommended for me, if it says recommended for you, right? Why would it show me a female jean if it thinks that I'm actually a male? The other thing that was actually really rather sort of unfortunate was that it would show expensive items along with discounted items almost next to each other. So as you can see, we have some products which are discounted and some products which are full price. And one of the things, like when we talk about sort of the brand voice, when somebody walks in to your store, or when somebody lands on the homepage, they're coming in the store with an intent to purchase, and then just showing them like discounted products at that point is not really the best, most elevated brand experience. So that was also one of the things that our brand partners within the company wanted us to change. And so the V1 architecture sort of looked like this, where we would effectively make a call to an endpoint, and then that would send us the recommendations back every time somebody landed on the website. The issue there was that it was not very configurable from our standpoint. If we wanted to make changes to the behavior of the recommendation carousel, we could not. The other thing was that there was a 24-hour lag time for the recommendations to be updated to a person's browsing behavior. So let's say I land on the website today, um, the recommendations will only be personalized to me tomorrow. Now, if you think about it, most shopping sessions probably don't last 24 hours. People probably browse on their phones or their laptops or whatever, and then maybe they shop for a few minutes and then they move on to something else. And if we can't really capture them uh, during that session, the opportunity is lost. And so we really wanted to move away from this 24-hour lag time and the lack of adaptability. And hence we decided we want to build something in-house. So the first approach we took was to look at using Amazon's Elasticsearch service. Now, Elasticsearch, as the name suggests, is actually is a tool that's primarily meant for enabling search. Just like for example, Google enables web search. Elasticsearch helps you. It's a platform that helps you enable search on on a website or any tool really. And if you think about it, actually recommender systems and search engines are both actually part of the same class of algorithms, which are in the information retrieval family. Effectively, recommendations can be thought of as a learning to rank problem, where what we're trying to do is that we're trying to say that based upon what I know about a consumer, based upon their browsing history, based upon their shopping history, etc., what are the most important products that might be of interest to them. So I think going back to Chaitanya's point about library books, if I know what books you've read, what are if I had to sort the list of books for you that might be most relevant, what would be the right order to sort them in? And so search engines and recommendation engines effectively try to solve the same problem. And so we thought, maybe Elasticsearch is a good way to start because it's a great search engine, and it's really meant to solve the learning to rank problem. And so we started off with that Elasticsearch, and what would happen is that our product attributes would come from Hybris, which is where our product catalog is stored. And then Elasticsearch would, we would use different algorithms within Elasticsearch to then, use the product descriptions as the document, and try to find similar products based upon the tokenized product descriptions. Now, this experience itself, I think, when we looked at it, I think it was a good proof of concept, but there were a number of issues with it. The first one was that there was very little adaptability because, again, we were using something out of the box, and for us to be able to make any changes on top of it, we had to write a lot of code that would take the recommendations from Elasticsearch and then rank it ourselves. And that wasn't necessarily the best thing. The other thing was that product descriptions are, themselves don't change very much, but there are other attributes, for example, like the price of the product, which does play, quite a bit into the relevance of whether the product is related to one product or not. Then there are other attributes like color, and there are attributes which are not necessarily contained in the product description, which then become a little bit tricky for us to incorporate as to that, what is the importance of a specific attribute as compared to a different one. So whether the color of a gene as an attribute is more important than, let's say, the leg opening for that gene. And so what happened was that Elasticsearch itself was not out of the box, was not necessarily the right solution for us. And so then we moved on to the next version, the next architecture, which, as you can see, is getting significantly more complicated. In this stage, we basically set up an Amazon API gateway that would connect with our the front end from the website, which would then, every time we received a request from the front end, would write that into DynamoDB, which would once DynamoDB, I think it's primarily used as a database, but it also has a queuing system. We use that as a queuing system to then trigger a Lambda job that would talk to Redis, which is where we're using Elastic Cache on AWS to actually retrieve the recommendations and then send them back to the end user. How we actually implemented it was we, again, used the same thing where we would take the product catalog from Hybris, replicate that into Amazon Redshift. We would run different algorithms in batch on Amazon EC2 that would, perform the matrix factorization, the collaborative filtering, and then generate the candidates for the candidates for the candidate recommendations for each consumer, and then we'd write that into Redis. And then as the consumer would shop, we would get the clickstream data through Segment, which is basically a online analytics platform that would help us understand what the help us understand in real time what the customer browsing behavior is like. We would push the events into an SNS topic that would be sent to another Lambda process that would then write the consumer shopping clickstream data into Redis itself. And Redis was really like our primary database as well as our cache. And then this process here would parse the consumer history, shop and clickstream data, and then rank the relevant recommendations, and then push them out. So our Amazon EC2 process was doing the candidate generation, and the Lambda process here was doing the actual ranking in real time. And then those were sent out back to the front end. Now, some of you who might have worked with Amazon's, products might notice that there are some inefficiencies in this process, and that was primarily because we were trying to put together something really quickly and trying to use technologies which we thought sort of were, would sort of get us unlocked really quickly. And when we tested this architecture out, it actually worked quite well. But there were some issues with latency, especially with Lambdas. And one of the things with Lambdas is that they have a cold start problem. So for example, if a Lambda is being fired consistently, then the response times are actually in the milliseconds. But if the events stop coming, then you have to warm up. You have to keep the Lambda warm for it to be able to respond to requests within milliseconds. Otherwise, it can take up to many seconds. And what was happening was that because the requests were taking longer than we would want them to, the front end was timing out, and then our error rates went up. And because of that, we basically moved to the latest architecture, which is a little bit of an eye chart, and I apologize for that, but that's really sort of an indication of the kinds of complexity that comes into the picture when you're trying to deploy something yourself. Um, and really, what we're doing here is that we take our data, transaction data from our order management system, and then our product catalog from Hybris, and then use DMS data, Amazon DMS, to then write that to Redshift. We then have multiple algorithms actually running on top of Redshift. So all these yellow cubes that you're seeing here, these are all different algorithms which are running on EC2, which are sort of doing the candidate generation, but using different algorithms. On similarly as to the past experience, we have the segment webhook that gets the real-time browsing data in. We write that into Redis, which again is Elastic Cache, where all the candidate recommendations are stored here. And then from that point on, we have an Amazon ALB instance, which basically powers a web server, where we have a Flask server with Waitress on top of it to serve the requests, where we do the lookup for each consumer and return the request to them. Now, even so the question could be, I think one of the first things people ask when they look at it is that, why did we go this route? And a big part of it was to have the flexibility that that we need to make changes. For example, if we get feedback from our business users, if we get feedback from our consumers as to if they want a different experience, we are able to change this very quickly. There's nothing here that's sort of that's limiting us in any way. We're not using anything out of the box necessarily. We're kind of using a lot of things, we are kind of like building a lot of things from scratch here to give us that flexibility. And the other thing is that it helps us support multiple algorithms that would help us create different types of candidates. And we'll talk a little about those algorithms in a moment. And the core value here is that there is no one size fits all algorithm that will create the right recommendations for each and every consumer. And what we're doing in our actual web service is that we look at what the consumer behavior has been, what they have been browsing, and then use that information to then um, rank the candidates in real time. And that really has helped us, not only create business value, but it also has helped us scale for very high traffic times when we have, for example, during sales, when we do promotions and sales on the website, when the traffic goes up, it scales. The ALB helps us scale pretty linearly, and we can actually switch out and add or modify algorithms as and when needed. It makes it super flexible. Plus, our response times have now actually dropped significantly to 250 milliseconds. And so our P95 latency right now is 250 milliseconds, which is faster than most web pages can load in any way. And our error rates have gone from, some very high number to like less than 0.2% or something. So it's almost gone now. And so that's really the power of I think I would say using something as flexible as the Amazon infrastructure, where we can sort of pick and choose the components that we need and then build them ourselves. And the other cool thing that happens with Dataiku is that all these boxes here, all these cubes, we can test all these out in Dataiku and see which one actually works for us. And when we test it out, then we can, if it works for us, then we deploy it in production, which is like a super easy process because it's really just, effectively it's promoting something that lives in Dataiku onto EC2. And so our code release and change management, code release and change management process becomes very much simplified. Because the DevOps people can also look at what's actually running on Dataiku. They can do their own performance testing there and then sort of give the green light to say that, okay, this actually works and you can use it. So let's look at some of the, let's take a little bit of a deeper dive into these cubes, these little cubes, and the algorithms that we are powering. And let's look at how they manifest on the front end. So the first one is a popularity-based recommendation model, which, as the name suggests, it's really recommending the most popular products to people. The way it works is, we look at what people have viewed, what they have liked, what they have added to cart, what they have purchased, what they might have shared with people. We have many different markers of intent from consumers. And then what we look at and see is that, okay, person A has liked, has expressed interest in a donut, in a cupcake, and a croissant. Person B has also shown an interest in a croissant, a soft serve, and a cupcake. So the most popular items here, as you can imagine, are a croissant and a cupcake, and those then get recommended to all of our other customers. And so it's a very simple algorithm. Nothing, no magic happening really. There's, it's as simple as it gets, right? And so we use this algorithm when somebody lands on the web page for the first time, and we have no idea who they are. We have no browsing history. They have not logged in or anything of that sort. And so what we do in that scenario is that first we change the title to say recommended bestsellers. What that does is that it clearly articulates the source of information. So the consumers can actually understand why is it that we are recommending these products to them. We also do location-based segmenting, where, for example, the moment you land on a website, your IP address is recorded, which can help sort of roughly geolocate at a city county level where you're coming from. And what we do on our backend is that we look at sort of what the weather is like, what might be the trends in that region, and then use that to then recommend sort of bestsellers for that region. As you can imagine, for example, in Europe, somebody who lives in Spain probably dresses very differently from somebody who lives in Norway or Sweden, right? And so we want to make sure that we take into account the regional preferences and then recommend bestsellers there. So this, when I took the screenshot from the backend, basically this was from somebody who was in a colder climate. This is a few months ago, older. So this was before we were having massive heat waves across, the world, the northern hemisphere, I should say. The other thing that you would see is that we show the men's products first, and then the women's products after that, so that there's no confusion as to why products are sorted randomly when people land on the website. The next algorithm is called association rules mining. And this is, I would say, the workhorse of recommendation systems, I would say, for the longest since the time that these recommendation systems existed on the web. And it's also a fairly simple and straightforward algorithm. What it looks at is what items tend to get purchased together. So for example, it looks at shopping carts of people. So when you look at the cart, it sees that person A purchased a donut, a cupcake, a croissant, and a soft serve together. Person B purchased a donut, I think probably a cupcake, a croissant, and a chocolate cake. So what it finds is that, oh, it seems like a croissant and a donut tends to get purchased together more often than other products do. And so the moment somebody lands on the website and they show interest in a donut, it'll recommend a croissant to them. And that's effectively how this whole thing works. And obviously, I'm simplifying it slightly, but you can think that's at a high level, that's really how it works. And so we use that for people who have just landed on the website and have started browsing, but haven't really logged in or have not really identified themselves in any way by adding items to cart, or just they're basically just browsing. They have not done any sort of high intent behaviors. They have not shown any high intent behaviors. So our headline then changes to say, because you shopped similar styles. And again, this is also the key intent here is to very clearly articulate that this is based upon your shopping behavior of the style of products that you have viewed. So we try to keep it very intuitive and very, sort of keep the headlines very simple. And we actually tested a lot of different variants with our copywriters and teams to make sure that this is the most simple uh, and intuitive tagline. So we spent quite a bit of time getting these resolved as well. And as you can see here, this person had actually browsed a mix of women's tees and jeans, and hence we are showing them other products which not only leverage the association-based rule mining, but also then helps some outfitting options. So what we see is that this jean and t-shirt pair tends to go really well together. This tee and jean also tend to go well together, and this product is also similar to some of the things that they've viewed. So it helps us, based upon association rule mining, it helps us get to similar products, or find other products that might help them, in an outfitting to create an outfit. Then the next thing that we have is our item-to-item similarity-based recommendation model, and I would say this is like the workhorse for us at Levi's. This is where we tend to get most of our number of impressions of the recommendation carousel, and this is where like we find most people end up following and sort of end up creating most value. And really, what it is that it at a very simple level, it looks at this person has shown interest in a donut. A donut is similar to a cupcake and a cake, for example. A croissant, on the other hand, is a savory item, and so that's not similar to a donut. Where versus like a soft serve is similar to a macaron or macaron. I don't know. My French is not great. And so what happens is that if you're interested in items which are sweets, which are sweet in nature, then I might recommend other items which might also be dessert items, which might be sort of like sweet items. And so really at the core of it, what we're trying to do is to say, what attributes does this product have? And what other items exist in our catalog which have similar attributes? And so the way we look at it is to so when the person lands on the website, this is the kind of experience that they get. Firstly, it says inspired by your shopping. So again, we clearly articulate why this product is being recommended to them, and it's really meant to say that you have shopped these products, you have shown interest in these products, and we want to show you other similar products that are based upon what you've viewed. So this person has actually browsed, when we took a screenshot, this person has actually browsed girls' tees, and the common attribute amongst those tees was, so girls meaning like, little like kids between the age of 4 to 7 years old. Well, the prominent feature in them was that they were on a like sort of a monochrome background with a prominent Levi's logo in there. And that was a common feature between them. And so as we can see is that most of the time prominent when you look at monochrome t-shirts, like they tend to be white or black. And what we noticed was that when we built the recommendation system for initially, it would find similar products, and let's say if they browse a number of white tees, it would recommend just other white tees as well with with prominent logos. But when we actually tested it out, our merchandising team came up with the feedback, which is that, on a white background, showing white tees creates like a very sort of uh, it's a very monotonous experience, and it does, and we need to add some visual breakpoint to create some visual interest. And so hence what we did was that we added a diversity metric a product diversity metric in our ranking algorithm that would ensure that there is some diversity of products, where it's not just white tees on a white background. We actually add a black tee which sort of breaks this sea of white in the recognition carousel, and that actually ended up testing much better than previously. So I think some of you might be wondering as to like, how are we actually capturing these kinds of attributes? How are we capturing these visual attributes, right? I mean, monochrome background and a logo and color, etc. So there are really three ways that we're doing it. The first one is to look at product attributes directly. So right now, let's look at this jean, for example, that this model is wearing. This jean has a specific name. It has a gender. It has its material attribute, etc. So there's a number of attributes for this jean. And what we can do is that we can try to plot each gene on these attributes, which gives us sort of like on, if you think about it, on a 2x2 on like sort of on a two-dimensional plane. If we plot the rise of a gene, which is like how high up does it go on your waist, on the y-axis, and if you plot the cotton content of the fabric on the x-axis, we can plot each product that we have on this two-dimensional axis. And then let's say this pink point is the anchor product, the product that the person is viewing. We can then sort of draw a bounding circle around it and say that, show all the products which are within this bounding circle as similar products. So similarly, we could do something for the leg opening, whether this is like a boot cut jean, which is like has a very broad leg opening at the bottom, or if this is like a skinny jean, which is like really, where it's a very narrow leg opening on the y-axis, versus the wash, like is it like a light colored jean, is it a dark colored jean? So again, we can plot, all the products in these two dimensions, and then say this is the product that the person is at. You can draw a bounding box and get similar products out of that. Now, this approach itself, I would say, works to a certain extent, but it runs into problems really quickly. The first one is that we end up with what we call a sparse matrix, sparse feature matrix, where a lot of products will end up having the feature values as 0, because we have such a large number of products that we carry. Not everything will have an attribute value that's specified for it. And the sparseness, first of all, like when we try to do any kind of collaborative filtering on it, creates a bunch of problems. Like it becomes very, very sparse. The other problem is the curse of dimensionality. What this means is that if you have basically you know d dimensions or n dimensions, you need something to the power of you need something to the order of like n to the power 4 number of products or data points to actually be able to you know find similar products, right? Because what happens is that as your number of dimensions increases, the ability to find similar products, which based upon just Euclidean distance, becomes harder and harder. And then little bit of noise here and there can actually end up causing a lot of problems there. So we had to get across this cross dimensionality and reduce the sparseness. And hence what we did was that we looked at ways to get image embeddings that will not only reduce the number of dimensions, but also uh, reduce the sparsity of the feature matrices. So image embeddings, sort of as a concept, has been around for, I would say, for a few years, and it's like becoming almost like industry standard these days. And the way it works is, you have, take any large pre-trained network, like VGG, ResNet, AlexNet. There's so many networks. There's an entire model zoo out there, right? You can take any of these networks, and when these networks are trained, their core objective is to classify, what is in the image, the object in the image, right? So in this one, this network classifies it as, a panda or a raccoon or something, and each classification comes with a level of accuracy. Now this is happening. This classification is happening at the softmax layer, which is the final layer of the network where the initial phases of the initial layers of the network are trying to extract some generic features about the object, and the latter parts are trying to combine those features to find a meaningful representation that can be fed into the softmax layer to then get the class probabilities. What we do to get image embeddings is that we actually chop off the softmax layer and then just take the output of the penultimate layer, which is indicated in blue here, and this actually ends up giving you this vector. It's like a series of numbers that you can then use to sort of like either use dimensionality reduction using any of the t-SNE, PCA, UMAP techniques to then sort of reduce it to 3 dimensions and then just do cosine similarity on it, or you could just use the dense vectors directly to use cosine similarity, or you could do something on the order of locality sensitive hashing or different other different or Levenstein distance or anything else that you want to then get distance between products. So what that looks like, sort of on an applied basis, is that let's say you are let's say this is a product that the consumer is viewing at any, on the web page, and this product has its own embeddings, this vector of numbers, and you can think of these embeddings as almost like a zip code for a product. Now, a zip code by itself, is a bunch of numbers, which by themselves don't really mean anything. The value of a zip code really comes in telling you what other zip codes is it close by, are close by, and really it helps you figure out the distances to other zip codes. So it's really all about the relative position of this product in conjunction to its in relation to its neighbors. And so let's say this product has this zip code, and what we can say is that, oh, this other product that we see here has this other vector, which is, let's say, is another zip code, and the distance between these is 0.1. This other product here is, let's say the distance is 0.3, this is 0.4, and this is 0.6. And this is actual real output from our algorithm. This is not like it's not a made up thing. And I think you can look at it, for example, like this product has some couple of a little bit of distress, which are the holes here in the knee, and you can see this other product which is more similar, also has holes, but and is also like a cropped fit, and also has like a wider leg opening. This one has significantly more distress, but as compared to this other gene, that's why the distance is a little bit larger. But the color of the gene and the the leg opening are also very similar. And so effectively, like you can you can look at these and then kind of like make meaning some sense of like what might be happening there. And so that's what we, so how do we create that? So what we did was that we used ResNet, which is like, a popular large network, um, which, sort of is used to, classify objects, on the image and data set. And so we took the network and we froze the weights of all the layers in ResNet and, added our own dense dropout layers on top of it, on top of the, we removed the softmax and then added our layers on top of the penultimate layer, and then fed our own data set with only about 10 categories of jeans, jackets, etc., and gave the task for it to classify whether this is a jean, whether it's a top, whether it's a short. And then once we got good enough sort of accuracy at K, when we found that it was doing fairly well there, we basically chop the softmax layer off and then get the embeddings out of the final layer. Um, so that's one way of doing it. The second, so sorry, that was the second way. The first way is that is to use the product features. The second one is to use visual similarity using the computer vision algorithms. The third one is to actually use the document similarity. A document here is the product are the product description, and we basically take the product description into as an input, put it through a TF-IDF the vectorizer, and then get sort of again an embedding for the document. And TF-IDF is basically a way to find out what words in this specific product description stand out and which uniquely help us identify a specific product description over another one. So like, for example, words like the and a, they occur almost in all documents, so they get a very low weight. But if a word like puppy shows up, then that's a rare word, and then that sort of characterizes the document, so that gets a higher weight. So we can do exactly the same thing. We get the embeddings, and we can find similarity, and then we can also use word2vec, for example, to then say that what are other similar words that can help us locate similar documents and similar products. The thing with word2vec though is that word2vec was trained on sort of on a standard Wikipedia corpus, but our corpus is actually significantly different because we have terminology that is not necessarily commonly used. So, for example, if you entered the term high-rise in word2vec, you would get similar words, which would be skyscraper, buildings, etc. But in the denim side, high-rise actually means a specific type of jean which goes up, quite significantly above the waist. And that's a very popular fit. So we have to be able to identify it correctly. Similarly, whiskers, on the other hand, mean something else, like which like it's like considered like but on a jean, it's this creases that come with wearing the jean often, right? So those whiskers these patterns need to be identified as well. So what we did was we actually trained our own custom word embeddings, and for that we again took a standard language model, which in this case was glove embeddings, and then the way the language model, what you do is that you basically train it on, you take the pre-trained model and then you try to predict the next word. So you started off with a prompt, let's say by saying that this gene is, and then you try to see how well it can do in terms of predicting what the next words are. And then once you do that, then it actually trains upon these embeddings, and it can give you like very similarly to how image embeddings works, like other products which are similar to this new product. And the last one is collaborative filtering. Again, this is again very standard algorithm, and this is primarily based upon understanding, if you have bought certain items, and then then looking at which other consumers are there out there who might have purchased similar items, and what else have they purchased, and then recommend that for you. And so effectively it uses a matrix decomposition method where if you have not purchased or shown interest in certain products, but other people have, then it finds other people who have similar taste as you and then recommends products based upon that. And how that ends up looking is on the experience side is that it says because you bought similar styles. And again, we try to keep the information, the source of information very clear. And then this person actually had purchased a lot of different men's and women's products, but they had primarily purchased denims. And so we first recommend a graphic tee and then for women, and then recommend other graphic tees for men. And this was primarily because of the purchase on jeans. The cool thing is that, all this is actually live on the website. It's part of an A/B test right now that we're doing. So, your experience might vary when you go on the website, depending upon if you're the controller test group, but you can go and try it out on the Levi's website. It's all there. And the final thing I'll end up with from my side is that, really, when you think about recommender systems and building any machine learning application, I think a lot of times we get very sort of excited about, as data scientists and machine learning engineers, we get really excited about the technology. But I think really, as Chaitanya said in the beginning, we have to start with the consumer experience and work backwards to the technology. And I think that's really what ends up giving you the best consumer experience. So with that, I'll hand off to, I think, Chaitanya.
Yeah, thanks a lot, Pallav. That was a fascinating and interesting journey through the recommender system land and algorithms. And thanks a lot for giving us a glimpse behind the scenes actions of running a real-time recommender system in production. So we have a few questions, and I'll give you like a few minutes to breathe. And I'll direct my first question to Data IQ, Will. Um, so with these kinds of projects that are being executed, would it make sense to simply hire an expert who can complete the full cycle of a data project?
Yeah, I think that it's definitely tempting to think about kind of this unicorn data scientist, machine learning engineer. But I think the way we see it at Dataiku is that you already have a lot of talent on your own team, and maybe that talent doesn't have a PhD in machine learning, but that talent does know your data, and they do understand the business needs. So I think I would recommend, really looking internally first at your team, and then thinking about the breadth of great technological solutions out there. AWS and Dataiku being some of them, but you're right, there are others as well. So I would say look there first, and then if you feel like it's really a skill problem internally and you need to bring on others, then go there. But first, try to leverage what you got.
Thank you. Um, how did you, could you please talk about how did you leverage AWS to enable machine learning at scale?
Yeah, for sure. So, I mean, one thing that should be noted again about the Dataiku data science platform is our agnosticism with regards to storage and compute. So we're a platform that enables all these individuals to come together to do things exactly like what Pallav just described. But so in terms of some of the AWS services that we work with, so if you're looking for instance, data storage, well, you're probably going to think about SQL databases like Redshift or RDS. Or more broadly, if you just want some sort of object store, of course, we integrate with things like S3. And then once you have access to your organization's data, you're going to need to run jobs. So we oftentimes will, think about probably single node model training on a Dataiku server. But if you're looking to do something else in terms of training, we also integrate with things like AWS ECS, so containers, Elastic Container Services, or more broadly, thinking about running training on EKS, so using AWS's Kubernetes services. And then also it should be noted too that AWS's EMR, so Elastic MapReduce, is something that many of our clients will use to leverage AWS's Spark capabilities and Hadoop capabilities.
Thank you. One more for you, and then we'll get to Pallav. So an inclusive and collaborative environment brings many people into the mix on a data project. How would you suggest monitoring the transformation of changes made by all these people during the project lifetime?
Great question. So I think if you want to think about monitoring and tracking changes in kind of broader data science governance, there's a few things that you need to do. So first of all, you need to have the technical ability to do it. And so in Dataiku, we give you one shared platform where individuals are all collaborating and working together. And obviously we have rigorous change tracking and version control capabilities within our platform. So whatever sort of technological solution you're using, you need to have the ability to very literally track those changes and understand who's doing what and when. And so we definitely enable that. But I think also one thing that we find, or I should say our clients find, is that this is very much a human process as well. So you also need to have human organizational protocols in place about how you make decisions, how you track these changes, how you promote work from kind of a dev test prod environment. And so I think it's kind of a two-pronged approach. Do you have the technology in place, and then have you done the thinking internally to really be rigorous about project monitoring and project deployment?
Thank you. Thank you so much.
Yeah, thank you.
Pallav, um, how did you measure the improvement on your journey through various versions of recommender systems at Levi's?
Yeah, that's a great question, Chaitanya. So I think one of the first things we looked at was the actual performance of the recommender system, and performance here meaning sort of more in terms of latency, error rates, stuff like that. And so that was, like, I would say, primarily what we were looking at, because we have pretty clear requirements from the front end team about what the performance needs to be and how much it impacts the page load times, etc. So that was one area of it. The other area of it was to actually have our merchandising team, our product team, our marketing team, and all the people who you would say are like sort of more uh, sort of conversant with our products, and sort of have some kind of a visual understanding of what the experience looks like, and then also our store associates, have them use it and see, as they browse, like, see if the recommendations are actually reflecting to a certain extent what they would have recommended. Now obviously nobody has has a view of the entire product catalog, and so we also looked at sort of, is there like that element of serendipity in there. The other thing that we also did, so that was like more on the qualitative side. Then on the quantitative side, we looked at, I think our primary metrics were intra-list similarity, and also coverage, catalog coverage. And so, for example, if if somebody browses three items which are similar, how similar are the items in the recommendations? And because we have the features, we can actually then measure that. And then on the other hand, if I have browsed sort of a wide variety of things, how much of the catalog coverage can I actually obtain in there? And we also looked at other metrics like mean average precision and like NDCG, etc. But I think those were, to a certain extent, they were not necessarily as indicative of the recommendation system's performance, because we had to add in other factors like diversity of products, and sort of adding some of the other rules from the business side, which would be, let's say, things like don't show um, you know discounted items at on the homepage, for example, and that, so then we couldn't necessarily like train our algorithms just based upon those metrics. So it was, we just kind of used, I would say, interval similarity and catalog coverage in terms of the more algorithmic metrics.
Thank you. I think this is turning out to be a very nice benchmark system of how real world recommender systems function, how they evolve, and how the metrics evolve with the business problem. That's really great. Thank you, Pallav. One more, please. Do you use this recommendation system to launch and feature new products, or make changes to existing products?
No, at this point, we don't necessarily look at it in terms of launching new products, because again, at the end of the day, if a new product is something that a consumer might be interested in, then yes, it's a great way to show that. But we do factor into account the newness of a product. So let's say, when we're doing popularity-based, recommendations, if a product was just launched yesterday, there's no way it could have the same amount of clicks and views, etc. So we do factor into account the newness, and the business users can actually provide a boosting sort of score for products that we can then use to say that, okay, this product was launched yesterday. It's fairly new, but business wants to promote it, so we'll boost it up. But unless it actually does fit into the person's taste, we don't necessarily, just show it just because it's a new product. So we try to keep it. We try to. It's a fine balancing act between keeping the business happy and keeping the consumers happy as well sometimes.
Thank you so much. I would like to end with a question to Will again. And now I would like to switch industries for a bit and move on to the FSI vertical. So the question is, security and governance can become an issue in certain industries, that is finance, in including various members of a team. How do you remain inclusive in these industries?
Yeah, great question. I guess I would kind of answer in two ways. So I think maybe at the heart of this question is the idea that when you have strict security and governance standards that, allowing too many people can lead to security breaches. And so I guess, first of all, of course, you need to have security, right? So first of all, things like secure data storage. So if we think about the AWS world, right, who has permission to what S3 bucket? Of course, you need to have those roles rigorously defined within your organization. And then, with regard to permissions and computation, you need to have fine-grained per user permissions on the data and on the compute resources. And so a platform like Dataiku will enable administrators to, dig into the weeds and make sure that at a fine-grained level, user A and user B can only see what the organization so intends. So that's no doubt important. But I also do think, again, that this call to inclusivity, even in these, what I'll say, sensitive industries, I think the call to inclusivity is still appropriate, right? So I think we are aware of some of the ways in which AI has misstepped in the past. So if we think about the ways in which potentially, biased AI solutions can be deployed and that can really be counter adding business value and adding value to our society. We definitely, I think, all want to avoid these things going forward. And so the more you have people in the room, I think the more we're going to add these appropriate checks and balances. So at Dataiku, we definitely understand the need for appropriate security, governance, and restriction of access. But at the same time, the more you can give the right people the ability to collaborate, and I think the more we're going to lead to solutions that really benefit others as opposed to potentially having this unanticipated but adverse effect.
Thank you, Will. It sounds like a well thought out, well engineered, and a product that is evolving continuously and doing all the right things. Thanks a lot for taking us through that. In conclusion, I would like to thank you all for attending today's webinar. I would like to especially thank Pallav Agrawal from Levi Strauss and Co. For taking us through a tour of the recommender systems in production. And I would like to thank Will Novak from Dataiku for taking us through a tour of Dataiku platform and its capabilities, and to both of them for answering our questions in a detailed and thoughtful manner. We look forward to supporting you in current and future projects. Thank you again, and have a great day.